That's what I want.
What I want you guys come on. What I want you guys to think of are, like we did yesterday, we thought of perfect squares. Today we're going to talk about and think about perfect cube roots. So we do the same basic idea where we're going to create a table, pick values of x that generate nice clean numbers for cube roots. So what's the first perfect cube?
8.
How about 0?
Oh, yeah.
0, 1, 8.
0, 1, and 8. Good.
You're a little ahead of yourself.
Now, if I do 27, is that going to fit on my 10 by 10?
Yes.
No, but I could go the other direction. I could go -1 and -8. So what I want us to do is this. I want to make, for a cube roots, I want us to go -8, -1, 0, 1, and 8. And that'll give us an idea of what everything is going to look like on both sides of the y-axis. And we know that -8 and -1 have perfect cube roots. We know that 0 is perfect cube, and so on and so on. So the cube root of -8 is -2, -1, 0, 1, and 2. So when we go to plot these, when I go to plot this one through, bonjour, no. Mr. Cooper. When I go to plot these through, I just start. -8 and 2. -1 and 1. 0, 0. Sorry. Sorry about that. I flipped on the wrong side. And your basic idea of a cube root function is increasing from left to right. It's doing that. X.
Is there an answer to
So basically, we do the same thing we did last night, just with cube
Yeah.
roots and-
Yes. Now, obviously here my a value for this problem is set up as a 1. And then if you have a scalar, you would just multiply your y values here by whatever the scalar was to make it move up faster or less. It could have reflected by making it negative to change them back and forth, just like they did yesterday. Yeah, it's a whole lot of dance moves going on here by all the different stuff. H is move it left and right, K's move it up and down. But every one of our graphs is going to have the same sort of start. Basically, we start by -8, -1, 0, 1, and 8, and go from there. Okay? So let me give you an example. Bless you. So let's go with the graph y equals -3 times the cube root x plus 4, all subtract 8. Did I say 8?
Yeah.
I meant 2.
So I was like,
I was wondering why everyone looked at me like I was really, I know I'm an idiot, but I didn't realize I was that big of an idiot. You guys all look at me that quick. I'll get over it.
I'm sorry.
So it's okay. So my a value is -3. My h value is what? -4, good. My k value is -2. Now, get in the habit at this point, guys. You're moving left and you're moving down. It's not a bad thing to do that. That way you don't screw up later on when you're looking at your h and k trying to remember what it meant. Pick your points. Well, I know what I'm going to pick. So the cube root of -8, -2. Yes, ma'am.
How many points do we
I want, when you do cube roots, I want,
do? Us to do 5 for cube and then 4 for square?
yeah. I think that's fair enough. Yeah. the h.
Yeah, but like, oh, wait, but I didn't know what was there. Like I was doing it where,
You were making perfect squares, weren't you?
yeah, I was making it perfect squares, like
You weren't doing it. You weren't doing it wrong. This is more complex when you get cubic, so you have to make a perfect cube.
Yeah, so like,
Watch what happens. You might be pleasantly surprised that you did okay. So what's negative? I'm sorry. What is the cube root of negative 8? What's negative 2 times negative 3? 6. Cube root of negative 1. Negative 1 times negative 3.
3.
Next one is? Next one is? It's nice how things are symmetrical like that. It's very convenient.
so would you just be able to get like the first 3 and then be like, okay, I don't need to do the other 2?
A lot of times. But it doesn't hurt to check it, make sure you didn't screw up something else. So now I go and plot my parent graph. Negative 8 and 6.
So if you get something that doesn't
Negative
work,
1 and
you
3.
Have you done good if you did that wrong?
I'm sorry, I was talking about something else. What?
Sorry. Like, so if you get for like the y values, if you get like something that's not mirrored, it'd be like mess something up.
Probably. So there's my parent graph. Remember, parent graphs are just there to help you visualize a generic sketch of what it should look like. So that's why we do it as a dotted line. Okay. Now to each of these points, yes ma'am? For these, yes. Because you have the cube root of 0 thrown in there. Same thing with the square roots. Our square roots always started at 0, even though with an a value, because 0 times our scalar is always 0. It's a good pickup. Because doesn't a slope equation, if it has no shift, always go to the origin? That's where this all comes from. To each of these points. To each of these points, we move left and down. 1 little, 2 little, 3 little spots, 4 little, 1, 2.
Do you want us to do that during the test?
In your head, would be great.
Okay.
So you go.
Oh, I meant like to graph the dot on the outside of the graph.
Yeah. That's
Yeah, do it in your head on the test.
Yeah. Because I really try to make sure that all of a sudden you guys are all going. Or
Hey, what's on your hand? 5.
That's funny.
so now we go. So now take a look at this type of a function. Is there any parameters that is making a domain, a possible domain or range restriction?
Wait, can you say that
One more time.
No.
Is there anything on this graph that shows a domain and or range restriction? No. This is what we call continuous. Every value of x that you choose, any real value of x is always going to spit out some real value of y. So for both domain and range here, it's all real. And that's going to happen with cubic or cube root functions.
All cube root
You have to really worry about domain and range restrictions with square roots because you can't, or fourth roots and things like that, because you can't take the square roots of negatives. Yes, sir?
So, like, even roots is fine. I think even roots got
So if you had a fifth root, you know, you could do the same idea, it just gets even nastier. Okay? Are we okay on that?
Yes.
What's wrong? You're abnormally quiet. It's like you want to say something, but you're not sure what to say.
This makes sense.
Oh, for the domain.
Oh, jeez.
Are you sure? Okay.
Great guess.
So what I did yesterday, that's awesome. It doesn't want to work like that anymore. What I did yesterday, which some of you guys might have heard about, is that I did post out some review stuff. I emailed this out to you guys. Emailed it to you, emailed it to your parents, posted it on the calendar. I made this quick little PDF file, and I have got a copy here for you guys too. I even made a note for myself to make a PDF. Oh, you did? Oh. I've heard a couple of stories because I sent along. I like to send along kind of snarky emails because I think it's funny. And yours, yes. Don't you ever read your emails?
No!
Read your
I haven't read the email in like 10 years.
How do you guys not read your email? It's why you guys have computers.
I read it before I got this. The time was just like
I mean, I would say that. It's just not part of my...
What's that? This stuff, yes.
It's just not part of my daily habit.
So, yes, sir.
I am, and like, as well as like everyone who's not gonna be here next week, still taking the test tomorrow, right?
Yes, sir.
Okay.
So,
No, you don't have to take it.
what I've done, and I have a copy of it here for you guys as well, is that I came up with some kind of generic problems of everything that we've gone through so far in this chapter, whether it's graphing, function notation, inverses, solving equations, all that kind of fun stuff. And what I wanted to do today was to get this into your guys' hands and kind of walk through a few things and kind of just show you guys, I mean, I'm going to leave the two, there's a couple of cube root functions on here. I'm not going to say, hey, do these extra ones out of your book. They're on this page. Whatever. They're on here, so I mean, they'll be on the test. So I mean, I'm going to go out on a limb and say this is probably one of the easier things we've done, which makes everybody happy. So I'm putting it on the test, so it'll be there, so you should be happy about that. So the test then, when we get around to it Monday.
Well, someone first, like, yeah, well,
Seven and 4. Then again, because we're this put an order in his head. I'm going this way. I'm mixing it up.
Oh my.
Ow! You didn't throw it at me.
So, one of the things that I wanted to show you is that a lot of people have been having questions about when you have, when was it? There was a problem. Which one it was? Oh, if you look at number 2. When I look at number 2, I have fractional exponents and I have negative exponents. The instructions itself say that you should only, your answers should only contain positive exponents, no fractional exponents within the denominator. Now, when we do these things, I've kind of tried to make sure you guys, or push you guys in the same setup each and every time. When you do this, what I want you always to do first is take care of your numbers and then move things around so that they have positive exponents. So in this case here, I multiply my numbers together, move my positive exponents, and go. I'm going to show you a couple ways to do this. Now, at this point in time, you have no negative exponents. You have no fractional exponents. But if you look at your numerator, the numerator is a top-heavy fraction, which means it can be simplified further. That's where a lot of you guys tend to mix up some stuff. This can be further simplified because x to the 7/4 is the exact same thing as saying x to the 1 3/4. Yes, ma'am?
Wait, why did you multiply the fours together?
Because it's 4 times 4.
Yeah, because it's 4 times x.
It's 4 times that times.
Oh, so you just wouldn't move the 4x squared like down?
No, because what has the negative exponent?
Yes.
The 4 is happy.
Oh.
Okay. So this case here, this is the same thing as saying x to the first, x to the 3/4, by simplifying that out. Now, what some people do, which I think is not a bad idea, if you have a string across right off the beginning here, you know you have two same bases, different exponents. What would you do with same base, different exponents to start with? When do you add them, multiply them, subtract? You combine them, you add them together, okay? So one of the shortcuts of doing this, well, here you have over x squared, y squared, this becomes, and this goes away, your final answer would be 16x 3/4 over x, y squared. You get that. And that's the correct answer because you can simplify out one whole out of the 7/4. The other way to start the problem is to, again, put your numbers together. X to the -2, x to the 7/4. If I add those two together, I get x to the -1/4. And then I have y to the -2, bless you, which gives me 16 over x to the 4th, y squared. And now from here, you would have to rationalize. How do I create a whole from a 4th? How many more 4ths does it need? 3 of them. This is where you would multiply top and bottom by x to the 3/4. 3/4 and a 4th create a whole. There's your x squared. That is 16x. So there's two ways to set these types of problems up. The first way, you just have to be careful when you have a top-heavy fraction within your numerator or a top-heavy fraction in the denominator and whole numbers on the other sides. That means something can be simplified. So always pay attention whether or not you have another extra step thrown in there. A lot of you guys tend to forget that there's an extra simplified thrown in there. Yeah.
Will we be getting our quizzes back?
Yes, I'm going to get them tomorrow because I think you were the last one to do.
What about everyone who's taking the test?
I can't push them out until everybody gets done. It's the way, nature of the beast. So we go from there.
Is that the
Yeah.
you simplify the x 3 over 4?
Then you get in the vicious infinite loop. If you simplify those back out, then you wind up back again at x to the 1/4 in the denominator, and then you have to rationalize it, bring it back up, then you go back.
Well, if you bring it up, you just
No.
No, because then it would be x down there and x 3 over 4.
Yep.
Are you just like yesterday?
Guys, hold on.
The 4x to the -1/2 times the 2x to the -1/2 to make it a positive exponent?
Hold on. 2x 1/2. No, you don't make those. Don't become positive. Same base, different exponents. When you're multiplying, you add the exponents. Okay, you add your exponents in this case. So you wind up when you do this one, you're going to get 8x to the -1, y to the 4/2, which is 2. This becomes 8y squared over x. What you're worried about is the power to power rule. And if you flip over to number 10, that kind of gives you an idea of what that would look like.
I was also excited for this test because I actually understand what I was doing because he
So in this case here, you can do a couple of things right off the bat. I know that everything in the numerator has to be raised to that 5/4. So there's a whole power rule going on. But I also have 2 sets of x's and 2 sets of y's. I can go ahead and combine them right off the bat, because especially with the x's, because they already have common denominators. If I combine what's inside here first, 5/3 plus 4/3 is how many thirds? 9/3 is how much? 3/4 and 3/2 is the same thing as saying, well, 3/2 is the same as 6/8. No, I'm sorry. 6/4, excuse me. So 6/4. So 3/4, 6/4 is 9/4. Okay. I'm sorry, what's that? We are. The only reason why I'm making it, that we don't have to do it all these fractions. I knew that I can just add those and just making it a little bit easier to start with. That's all. And then I have to do that to the 5/4 over x squared y to the 4/3. So now you have that power to power rule. When you have power to power is when you multiply your exponents. So 3/1 times 5/4 is x to the 15/4. Y then to the 45/16 over x squared y to the 4/3. Okay? I see a bunch of fractions in the denominator, so and things I could probably simplify. Because if you look at the numerator, you've got mixed numbers. I'm sorry, you have top heavy fractions that would generate mixed numbers. So I want to kind of rewrite these to try to see what I can simplify out. 4 goes into 15 how many times? 3 of them, and then how many are left over? 3. So this is the same thing as saying x to the 3rd and x to the 3/4. Okay? I broke it apart. Now you can do it that way, or generate the x squared in terms of fourths and play war. There's a couple ways of doing it. 16 goes into 45 how many times? 3 would be 48, so it's twice. So that's a y, so twice, then be 30, and then 13, I believe? So it's y squared, y to the 13/16. Now, again, the reason why I did that is because I know that I can simplify an x squared here. All right, I can get rid of an x squared. Y to the 4/3 is y to the 1st, y to the 3rd. You okay with that? So I have a y and a y to the 3rd, which means I can get rid of a y here and one y here. Now, in order to rationalize this, all I need to do is come up with how many more thirds out of the denominator. 2 of them. So I'm going to multiply the top and bottom by 2/3. Y to the 3rd times y to the 2/3 makes a whole. So I have a denominator now of y. The numerator gives me x and x to the 3/4, depending upon how the answer, if you break it apart and you leave it like that, it's really not the end of the world. Or if you go back into the full fraction, that would have been 7/4. And now here, I'm not doing that in my head. I'm going to use a calculator. Okay, I'm going to type in my calculator 13/16 plus 2/3 and hit enter. And it'll give me a fraction with probably a denominator of 48. There you go. Is that right? Ooh. Wait, how did I lose a Y?
Yeah, that's what
Because there's a Y in there.
Yeah, because there's a Y.
Because there's a Y, yes, and now there's, good call. I didn't see that right off the bat. Now I can get rid of one of the Y's out of this one.
The 71 divided by 48 is 0.
What's this one?
140.
No, because then
It's
this
like
one should be here,
1.47
1.4.
something, whatever.
Did we add in the other one? Because it was a Y and a Y.
Yeah.
You crossed up 2 over 1. That one.
Yes. No, because this generates the 1. I wonder if I wrote something down wrong somewhere along the
You
lines.
know, you got the answer right, except it's not over the Y.
Yeah, I'm trying to figure out where I got the.
Because you gotta pull, you can pull a Y out of the top, like the fraction, and then you subtract it from both the top.
No, because this is the correct part, but I'm trying to figure out where I got rid of, how I didn't get rid of an extra. I must have forgotten to get rid of a Y somewhere.
No, you did not a Y. The Y is squared, it says base scratch out and you missed that one. You forgot to carry that one across.
Oh yeah, and then you would take out the Y.
No, up or
Go
Oh,
up,
up
yeah,
one.
yeah, forgot that
Oh,
one.
yes, thank you. You're right, because I forgot to bring that one to here, because I had that one, then those would have gone. Thank you, I missed it.
Okay.
I missed that one that I already took apart, so I missed it at the beginning. Okay. So, yeah, they can get a little messy.
You don't want us to take out like the x and then an x plus the 3/4.
No, because now at this point, there's no reason to try to do any of that, because you got nothing left in the denominator to simplify out.
Okay.
Yeah, how do we get 71?
There's gonna be a lot of space for like, alright.
I added these two together.
Oh, I would think you would multiply together.
When you have x cubed times x to the 7th, what is it?
Oh.
So it's just x to the 13 16th and x to the 2/3. It's just really crappy looking numbers.
Okay, so you add the,
13 16ths plus 2/3.
That's bad, bro.
Yeah, except.
Like this. Wait, I thought you just did it.
No. What's x to the 3rd times x to the 7th? It's x to the 10th because you add them. Same thing. It's just a fraction. All right. The other one I wanted to show you really quick is that we have not seen an inverse written like this yet. Number 13 says find the inverse of this. Okay? It says find the inverse of that. Now, when you find the inverse of a function, especially when you have a fraction and they put that negative symbol in front of the fraction bar, does it matter where the fraction bar, where that negative symbol floats?
No.
No. Normally what I would do is I would automatically float it to there. And then when you find inverses, remember, all you're doing is flip-flopping x and y. So x equals -2 over y minus 1 plus 1. And you're going to resolve for y. 13, I think?
Yeah.
Yeah.
You mean for X?
Now what do you want?
So what do we do?
What do you do? Well, what do you do first? What do you have to move first?
Plus
A 1. So how do I move this plus 1 on the end here?
Subtract it.
Subtract it. So now I have x minus 1 is -2 over y minus 1.
And then you multiply it by y minus 1.
Multiply both sides. Now, do you remember this little trick from similar figures? Whenever you have 2/3 equals 4/6, does everybody agree with that statement? Because it's a ratio, it's a proportion. A proportion is anything that says fraction equal fraction. Now, what you can do with fraction equal fraction is you can change them on the diagonal and still get a true statement. You can exchange anything that is equal fraction, and flip-flop along the diagonal, and it still works. This becomes really evident, and we did this last year in trig, when you did it in chapter 7 in geometry, when you had sine of something equals x over whatever. It was on the diagonal, you just flip-flopped them. It's the same reason, okay? So sine of 15 equals 30 over x. Remember we did 30 over sine of 15 equal to x because you exchange on the diagonal. This is the same thing. What we do is we flip-flop these two. Just like we were saying, Sarah, multiply both sides by the or y minus 1, then you divide both sides by the x minus 1. And it gets you there. And now to get get the y by itself, what do? Add 1. And if you look at it, where'd you wind up?
The same
Right
thing.
back at the
That is.
This happens to be, now the answer on the back is a little different because they floated the negative symbol to the denominator and then negated both parts of the denominator, which is fine.
It's the same on the back.
No, I didn't put a negative x plus 1 in the bottom
Oh, it didn't.
Yeah.
because they floated it differently. They floated the negative symbol differently. It's just, I press buttons. This is one of those weird cases that there is a possibility of having a function be its own inverse. Yeah.
So, like, with that case, it's like, I guess the answer on the back is right and this is right. Would there be like multiple answers?
There's more and that's why I wanted to show you is that especially when you have negatives, if they don't put the negative on designated where, it could float, and it just depends on how you float it. That's all. That's why one of the reasons why I wanted to show you that.
Except you know the one on the back.
No, you have to do exactly what my mind is thinking.
Alright. I mean, if I can like take your brain and like over through like the past, that'd be great.
Trying to think what else is there that I wanted to kind of show you. Your best bet, what I'd like you guys to kind of walk through as much as you can tonight, try and get as much, because I know how much you guys love exponent rules. Try and get through as much of the exponent rules and do a couple of cube roots real quick tonight. We're going to spend the bulk of the day tomorrow going over cube root, or making sure you can do the cube root, which I'm sure you did. And then we'll do a lot of time on exponent rules and going from there, okay? I will try and see if I can make up another version of this as well. If you guys really want more problems, I can post that over the weekend as well. And see what the answers and just go from there. But that's what I plan on doing tomorrow. I want you, yeah, try and get through as many of the exponent rule ones as you can, because that's what I know most of you guys have issues with. Okay. Yeah, I'll record what we do tomorrow.
Questions or on the?
I don't know.
Not sure yet?
I'm not completely totally done. I kind of have an idea of where I'm at. It's about 14-ish in that neighborhood. Yes, ma'am.
Was this the report for the test or the quiz?
Probably, yeah. Because Noah was back at
That was the
I
quiz
need to
one.
test review. If there was one for the calculator, not test.
He's getting another quarterback too. So.
What? Monday. There's a couple people that are gone next week, so I had to make another version.
Yeah.
It'll be on Tuesday.
What's the other Sunday, Monday, and Tuesday?
It'll be on the Monday we get back, or the Tuesday we get back.
I'm kind of hoping this one. I do like a I don't want to.